Okay, class, this is going to be video 3, and we're going to go through the ideal gases and ideal gas law, which is the tail end of Chapter 10's notes. So pull out your notes again. Real gases do not obey Charles' law and Boyle's law exactly. The gas laws do not govern how they behave, they describe them, and these laws are valid only under very special circumstances. An ideal gas, you need to understand this, is a gas whose behavior is perfectly predicted by the kinetic molecular theory. But no real gases are ideal. They just come very close. Okay? So they have to have, in order to be ideal, they have to just be perfect. They have to act perfectly. We're not going to worry about reading the sections in this video, but you can go to your textbook and look on page 272. And at the bottom, read paragraphs 1 and 2, or read, it has like a number 1 and a number 2, and it just talks about the ideal gases on those. I might read it in class. Now, remember that molar volume of all gases is 22.4 liters, right? Well, not exactly. That is just kind of a general number. The volume 22.4 is useful, and it's what we're going to use for all of our math, but it doesn't show reality. There are forces that cause molecules to attract together. The bigger they are, the more they're attracted to each other because of those forces we've talked about before, the intermolecular forces. And the smaller they are, the more likely they are to act more ideal. So here's where the ideal gas falls into play. And you can see some of them are a little bit, the volumes are a little bit larger, and some are a little bit smaller. So the ideal gas law kind of helps us to deal with some of this. And the ideal gas law says PV equals nRT. Okay? Now, we've been talking about ideal gases, and they have to behave according to the ideal gas law. It's here we're still kind of pretending that everything's okay, even though we know that it's not perfect. And you're going to have, if you go on, you'll deal with some of these exceptions in college, I'm sure. Now, the way these things are, N, it stands for the number of moles. P for pressure, V for volume, T for temperature. All those make sense. And then R is a constant. And don't ask me why they use the R instead of like a C or K. Well, I guess they don't use K because that's kelvins. But R is a universal gas constant. And there's a bunch of different options. You'll be given all of these. You're always given the R value. And I'm going to show you some options for them from the Prezi. Oh, that's not the Prezi. Here it is. There's all these R, universal gas constants, and they're different values. And the way you know which one you got to figure out which one to use. And the way you know which one you're going to use is you look at the unit. If you're having ATMs and kelvins, then you're going to use this first one. If you're going to have millimeters of mercury, you're going to use the second one. Torr, this one. kPa, this one. Your units have to match. The units in your problem have to match the R value, the gas constant value that you're going to use. So let's go to this first question. How many moles of gas, so how many moles, members, that's the N, of gas are present in 2.4 liters at 1.25 atmospheres of pressure? There's your volume, and 27 degrees Celsius, that's the temperature. Well, remember, always mark, I have a P, a V, an N, and a T. Well, what's the only formula that has all that? P, V, and N, and a T? Well, that's the ideal gas law. Also remember, too, that the temperature has to be in kelvins. So that's going to be something we have to change right away. So I'm going to do that, 27 degrees Celsius, turn it to kelvins by adding 273, because that's always how we're going to do it. And so that's 10, and that's 910. So that's 300 kelvins. And it's going to have a decimal point there, guys, because when we're adding, we're looking at place value. We have to go to the ones place, okay? We have to go to the ones place. All right, so now we have our temperature in kelvins, and we're going to solve this. PV equals nRT. PV equals nRT. And now that you remember that when you write the formula, that's the first point. That's the first point of your work. Okay? Now you're going to solve for N. Now we can go ahead and solve this equation for N by dividing by R T and dividing by RT over here, canceling out the R and the T, so that number of moles, the N, is left. So my new formula would be N equals PV over RT. So let's put in our values now. Pressure, 1.25 atmospheres, right there, times my volume, 2.4 liters, divided by R, I'm going to leave that for a minute, and divided by T, which is 300 kelvins. So I'm going to write that over here, 300 kelvins. So my R, I got to figure out which one of the R's to use. I have atmospheres and liters and kelvins. So if you went back to the present, you would be able to find the R value that we're going to use, and the R value we're going to use is going to be 0.0821, and it is liters, let's see, what was it? Liters times atmospheres, there it is, divided by moles times Kelvin. Liters times atmospheres divided by moles times kelvins. And I say I got to have all these units. You got to have all of these guys. Liters, atmospheres, moles, and kelvins. This whole thing is the R value that I'm going to put over here. So 0.0821 liters times atmospheres divided by moles times kelvins, which looks really confusing, but it's really not. We're going to just cancel out a bunch of junk. So here we go. We're going to cancel atmospheres, and look, numerator, denominator, atmospheres, liters, numerator, denominator. Now this is kelvins, but see this kelvins below it? So kelvins cancel. The only unit that did not cancel is moles, and that's what the N stands for, moles. So now we just have to do the math, and we can put this number in, and I'll put that in for you. All right, I did it. Now when you're doing this, be careful. You're going to say 1.25 times 2.4. You're going to divide by 0.0821, and you're going to divide by 300. So you divide by both of these numbers on the bottom. Make sure your order of operations are very careful. Now we have to look at sig figs again. So we check our sig figs. Let's see here. There's 3 sig figs here. There's 2 sig figs here. This is a constant, so it doesn't matter. And there were 3 sig figs here. So my answer has to have 2 sig figs. 1, 2. So it's 0.12 moles. That was our final answer. How many moles? 0.12 moles. All right, we're going to move to one more question. This one's just a little bit harder, so we'll work on it kind of slower. We have a 5.04 times 10 to the minus 14 kilogram sample of gas occupies 4.57 times 10 to the minus 4 millimeters cubed. This is volume. This kilogram is mass. Okay. At 9.63 times 10 to the 4th pascals, that's pressure, and 293 kelvins, that's temperature. Okay, what is the molar mass of this unknown gas? Okay, so this one seems a little bit difficult. So what you need to do is always put down what you have and try to figure out what you can use. All right, so I have a pressure, and our pressure is 9.63 times 10 to the 4th pascals. I have a volume, 4.57 times 10 to the minus 4 meters cubed. I have a temperature of 293 kelvins. All right, I don't have a second set of temperatures, and I'm not asking anything like that, but what can I do with this? Well, if I look at PV equals nRT, I have pressure, volume, and temperature, and I'm always going to be able to figure out the R. So the only thing I don't have is an N. I don't have the number of moles. All right, so let's figure out the number of moles. This is one of those times when you use a formula to help you get to where you're going, even if you're not absolutely sure what you're doing yet, okay? So I'm going to figure out the number of moles. I'm going to solve for N by dividing by RT again, so that now N equals PV over RT. And I'm going to put my stuff in. I've got pressure, 9.63 times 10 to the 4th pascals. Volume, 4.57 times 10 to the minus 4 meters cubed, divided by R, which I'm going to look at in a minute, and temperature, 293 kelvins. So now I got to figure out which R to use. I have pascals and meters cubed. Okay? Now, so I'm going to go look and see if I have an R that will work for that. I have here pascals and liters. Okay? So that looks kind of like it won't work for me, but it will. And I think in your textbook and in the I'm going to check in your textbook really quickly and see if it has the right ones, because there's a million different options here. So just in your textbook or in the reference sheet, you'll be able to. All right, so I was right. In your textbook on page 274, one of the R value options has meters cubed and pascal. So we don't have to do any unit conversions. We can just take this particular one that has all the units we need, meters cubed, pascals, and kelvins, and put it here. So we're going to have 8.31 meters cubed times pascals divided by moles times kelvins. Now, if you didn't find one that worked perfectly, you would have to do some unit conversions so that all the units end up working. So I'm going to cancel out units now. Kelvins and kelvins cancel. Pascals and pascals. Meters cubed and meters cubed. So moles is the only thing that's left. And I put it all into my calculator, and I end up with 0.0181 moles. And that's with 3 significant figures, because all these numbers have 3 sig figs. So that was my N. I was able to figure out the number of moles. Okay, well, does that help me? Well, the question is, what is the molar mass? Okay, what is molar mass? Okay, let's just write down what that is. Okay, hold on one second here. All right, well, the molar mass is always some number of grams per 1 mole. Okay, now we just figured out how many moles we have. So we have 0.0181 moles. How many grams do we have, though? Well, they gave us the mass up here in kilograms. So I just got to put the mass in kilograms and turn it into grams, which is just, another conversion. So 5.04 times 10 to the minus 4 kilograms. I have to turn it into grams. Remember, there are 1,000 grams in a kilogram. So we're just going to multiply this by 1,000. And then we're going to put that over here and use this number right there and divide it, and we'll get the molar mass. Okay? So let's pull this up. I'm going to just show it to you on the calculator so you can practice. 5.04, and then we're going to do second function again. Second function, double E, there's a little negative sign, 4, enter. And then times 1,000. There's your number, 0.504. So that's 0.504. 0.504 grams, because the kilograms cancel. So now it's 0.504 grams divided by moles, and that's going to give me the molar mass. 0.504 divided by 0.0181 equals a molar mass of 27.845. So 27.845. Look at sig figs, 3 sig figs, 3 sig figs. So 27.8, what's the units? Grams over moles. Grams over 1 mole. There's the molar mass of my unknown gas. 27.8 grams. All right, that one's a little bit more involved, but hopefully you can see what you need to do. You always look at what you're given and see which one of the formulas will work. What can you figure out from that formula? I can figure out the number of moles. How does that relate to molar mass? Well, molar mass is grams over moles. So I know the mass, and I figured out the moles, divide the two, and I have the molar mass. And that is the end of the notes for Chapter 10.